Welcome everybody to the OpenGL Barthold. My name is Barthold Lichtenbelt, and I chair the OpenGL working group. So here's our agenda for today. I'll tell you a little bit about what's new in OpenGL and what's in OpenGL 4.3. Bill will talk about cool things you never dreamed you could ever do with OpenGL. And our first guest speaker, Rich from BOF, will talk about the effort they've done for the Left 4 Dead 2 on Linux. Rich, where are you? He's over there in the back. And then we'll end with Akeley, co-founder of STI and co-founder of our API, to say a few short words about his perspective on 20 years of OpenGL. And we'll have a party afterwards. Also, we have some trivia throughout to give away, so I'll ask a couple questions after each presentation. Another announcement, there will be reference cards for you and t-shirts. But only if you play nice. That means one t-shirt and one reference card per person. And you can collect that once the party starts over there somewhere. You should have tickets, or you should be able to get tickets, one of our tickets from all this presentation going on, so you can get your reference card and your t-shirt. Surprises? Surprises? We have more OpenGL Inside books to give away. And I have in my hand a virtual NVIDIA Quadro capital-based graphics card. Value of $2,250, I've been told. Actually, I have two. So those are going to be very special. And you can turn this piece of paper into a real graphics card as soon as they're available. Right. Move on. So all of this party, the giveaways, the t-shirts, reference cards, would not have been possible unless we had a large amount of sponsors. So we have 16, I think, at last count, corporate sponsors, the logos that are here on the slide, that came together to make this possible. We also have over 30 individuals like you, many of you are probably here in the room, that donated money to make this possible. This is a constant going together of the community. It's great. I'm very, very impressed, pleased, and proud to see this. So applause for everybody here. In particular, I want to call out Cass Everett. Cass, are you here? Who was our largest single personal donation for this party here. So if you see Cass, buy him a beer. Okay, let's move on. Why are we here? Well, we're all here to celebrate 20 years of OpenGL. It's an awesome achievement that the technology can be relevant in 20 years later, even more so, even more relevant than it's ever been. Really, I call it a tribute to the architecture and the design of OpenGL that was done more than 20 years ago, and it's still relevant today. So thank you to everybody who worked on that. To put that in a little bit in perspective, 20 years ago you could buy a reality engine, well maybe one or two of you could buy a reality engine. And it could render 1 million triangles per second, the magic number 1 million. Today, you can get your high-end cell phone, it renders over 100 million triangles per second. And it does that in power envelope of less than 5 watts or so, whereas your reality engine did it in 1.5 kilowatts if Google is correct. We look at your NVIDIA high-end graphics card for your PC today, the GTX 680, which can render more than 1800 million triangles per second. Quite amazing achievement. So I had planned a demo. We had a little trouble showing some of the stuff here on the screen. So instead, we have an O2 in the back you can play with. It runs OpenGL 1.0. Real life, you can touch it, you've never touched one before and play with it. It's awesome. Okay, some updates for what has happened in the last year. Well, Doom 3 source code was released, where you can see now how Carmack did this himself. Of course, we all wrote about the Steam announcement coming to Linux, and that's why you're probably here, so no more words on that. Several books were released, including the OpenGL Inside book, we showed you. I think you can actually buy it today. Moving on, numerous tools were updated to OpenGL 4.2 and hopefully will be updated to 4.3 soon. Several new interesting projects came up. GeoCaps Viewer, an online database with capabilities of graphics cards and extension lists. Regal for OpenGL tries to bring the OpenGL 4.2 or 4.3 API to all platforms, Linux, Android, macOS, Windows, etc. Poland, C++ library for visualizing very, very large data sets. Pretty cool stuff. And then this tutorial caught my eye, especially if you're new to OpenGL, it's pretty interesting. It talks about OpenGL 3.3 and on. Of course, we're also here to celebrate and announce OpenGL 4.3. Yeah, that's what it's about. I've shown this slide every year to you now, but since 2008 we have released 7 specifications. We are keeping a rapid pace to give as much advanced functionality to you as rapidly as possible so that all these cool hardware gates are available to you and you can write these awesome applications for us. Again, 4.3 is the result of strong collaboration of a number of vendors. That includes, in random order, AMD, Intel, NVIDIA, ARM, Defense Gaming, Imagination Technologies, Qualcomm, and Apple, among others, all worked on the 4.3 specification. So what's new in OpenGL 4.3? It's a lot, so I'm not going to go all of it. I'm only going to go over the stuff that you see here in red. You can divide it up in broad buckets, if you will. Texture functionality, buffer functionality, new pipeline functionality, we have extensions, and we have a whole new set of features in the shading language as well. This slide is the OpenGL 4.2 pipeline, you probably all are familiar with. In blue are binding points, either buffer or texture binding points indicated with the red B or T. And then in this pinkish color, that is fixed function, and then in the yellowish color, that is programmable functionality. What's new in 4.3, we're adding another pipeline, the compute pipeline, if you will. A couple things to notice here. The compute shader has access to texture resources and buffer resources. The compute shader has no access to a framework. So you have to transfer your data between a compute shader, a compute pipeline, and a graphics pipeline through buffers. And most likely we're going to do that through this new buffer that's not up here, shader storage. And more on that in a little bit. The more on compute shaders. If you write a graphics program and you need to do a little bit of compute, say a post-processing effect, you probably want to use a compute shader. If you're a high-performance compute guy, you write very large kernels that run for a long time, and you don't care anything about graphics, you're better off using OpenGL. Compute shaders are written in GLSL, so the shading language you already know about. There's a couple of examples here in the bottom left. Image processing, this is computing a histogram of this image all in real time without ever going back to the host. The AI simulation, you could use a compute shader to compute the positions of these people moving in the scene. You can obviously do ray tracing, you can do better water effects, and my personal favorite, interactive global illumination, all done with compute shaders. Of course, a compute shader demo or talk is not complete without the obligatory particle demo. This was actually done by Dr. Mike Bailey from Oregon State University. He joined Khronos 6 months or so ago, and he's been very useful and very helpful in helping us understand the needs of the educators. And he has his own website here. He rendered these using the NVIDIA OpenGL 4.3 drivers that are now available. Okay, compute programming model. At the highest level, you start with a dispatch, which can be 1, 2, or 3-dimensional. In this case, it's 2-dimensional, 3 in the x direction, and 2 word groups in the y direction. Then, zooming into the word group consists of a set of invocations. Here we have 4 invocations in x and 2 in y. And then, there are built-ins in the shading language that are useful to you to understand how to maximize parallelism basically coming out of the compute program. Because all these word groups and all these invocations can or might run in parallel depending on the underlying graphics hardware. But to make this a concrete example, let's look at this invocation ID 2,1. Its word group size is 4,2. Right? This word group has 4 in x and 2 in y, total of 8 invocations. The word group ID this invocation came from is 1,1. And then the local invocation ID, so the ID of the invocation within the word group is 2,1. And then there's also a global invocation ID. There's a unique ID across all word groups in this dispatch, and that's computed out of the 3 previous ones. In this case, it's 6,3. Okay, memory hierarchy. We start with our dispatch again. And work groups. Work groups have read access to textures, texture buffer objects, and uniform buffers. We also have read and write access to images, data buffer objects. Data storage buffer objects, I mean, I'll talk about that a little bit more. Zooming in again, within a work group, all these invocations have access to shared variables. And within the work group, each invocation has access to its own local variable as well. You want to be careful here. Use barrier to synchronize invocations in a work group. And use memory barriers to order reads and writes accessible and visible to other invocations. So memory barrier was introduced in 4.2, I believe, with tesselation shaders. The rest there is all new, so memory barrier, atomic, etc., all introduced in 4.3. Also note that memory barrier shared and group memory barrier are only usable in computers. Okay, jumping topics to texture reviews. So what can you do with a texture review? The new one OpenGL 4.3. It really allows you to look at texture data in different ways. For example, you might want to look at RGB data in linear format, or you might want to look at it as sRGB data. Or maybe you have a whole bitmap chain, all these bitmap levels, and you want to pull one out. You can use a different texture view to do so. Note that there's no duplication of textual data happening here. And also note that we managed to do this without introducing yet another object type into OpenGL. So how does this work? This is something you should already hopefully be familiar with. We have sample objects, we have texture objects, we have textual data store, when the actual textuals go, and we have some texture lookup hardware. Of course, the sample object has sample parameters. Texture object also has sample parameters. Which ones are being used for the texture lookup hardware depends on the sample object development. Texture parameters exist too, for example, to indicate the width, depth, height of the texture. And the new is the concept of texture view parameters. These really tell texture data store how to look at the data and what to feed to the texture lookup hardware. So in this case, I have a bitmap chain of 4 bitmap levels. And the texture view parameters are set so that the whole bitmap chain is visible when used in texture lookup computation. Note also, you have to call the text storage API if you want to create a texture view. So now how do you create an actual texture view? Again, we have sample object and texture lookup hardware. And now we're going to create a new texture object. That's created with a new API called texture view. Aptly named. We have sample parameters, but note the sample parameter values, like the wrap modes, are all set to default. Same for the texture parameters, and also reset to default. And then the texture view parameters are unique, as you might expect. These are different than from the other object it was derived from. That's where you tell how to look at the textual data this time. Maybe you want to have a different internal format or a different bitmap level you want to pull out. In this example, we're going to pull out only one bitmap level. And then the texture view parameters itself are set with the texture view column shown here on the screen. Okay. Debuggability. We have our debug already. Provides very nice verbose output, what's going on in the program. It can give you errors, performance warnings, things like that. We've augmented that functionality. Previously, when you get this huge stream of data, there's a number in there, texture object number 23, who knows what it means. So now you can actually add labels to your objects. You can really look at the thing and say, okay, texture object number 3 is used in this scene for a reflection map, for example. Further, we have markers. You can stick a marker in the debug output stream and just identify maybe sections of your code. So within a frame, you might have several rendering passes, so you can use a marker, say rendering pass and one forward start here. You can also encapsulate sets of API commands in a group. And then within this group, you can, for example, control the verbosity output. So if you know this piece of code is already working well, you don't want a million lines of debug output, you just define a group, say verbosity low, and off you go. Multi-draw indirect, and I'm going really quick here, bear with me. Multi-draw arrays and multi-draw elements indirect are two new API calls that are really cool, I think. They combine the best of multi-draw and draw indirect. So just to recap, multi-draw gives the ability to render sets of primitives with one API call. Very low overhead for the application, very low overhead for the driver, just kick off the work. Draw indirect lets you or the GPU store parameters for the draw call in a buffer object. So the GPU can create work for itself, store parameters in a buffer object, and then with one API call that works and kicked up. So now we combine that and create a very powerful machine to create lots of work in the GPU, if you will. So how does that work real quick? So at the top in yellow here, either your program or a graphic shader creates all these parameters for these draw calls. Stores this in a multi-draw indirect buffer, in the blue buffer here. In this example, there's 6 sets of parameters in this pinkish color with the 3 dots in it. At the bottom you can see, zoomed in, what the structure is of those parameters. So these are parameters to a draw call. So with one multi-draw arrays indirect call, now you can kick off rendering for all these 6 and then render this cylindrical or this torus with this cylinder structure, if you will. Pretty cool stuff. Okay, shader storage buffer objects. This is a new type of buffer object. It allows you to read and write, especially the write part is interesting, to a very large buffer, at least 60 megabytes or maybe more, using regular array syntax in your shader. So it's a very natural way to read or write to very large buffers. I expect that this is going to be the default way of you transferring data back and forth between compute shaders in the graphics pipeline, just because it's so easy. And I have an example of this. In the next slide. So how does it work? Well, first, you create a buffer. As you all know, you probably know how it works. Then we stick some data in it and we make it active. Here we're binding it to arbitrarily picked index point number 4. So this new binding point shader storage buffer. In our shader, we're going to use the standard 430 layout. It's also new, introduced. It's even more tightly packed to create an array of structures called buffer. And notice the binding 4 here. Also in our shader, we can declare a simple structure with some vertex data in it. In this case, some texture data, a position, and some other data. And then we're finishing our array of structures. So notice here, it's an unsized array of structures. With the binding equals 4, we now just reference this buffer unsized array back to our very large buffer object we bound in the top of the slide. Of course, your shading needs to compute something, and then the last line is the key line here. We're using normal array syntax to write to this buffer object. Okay, new extensions. We have KXR extensions now. KXR extensions are extensions both approved by the OpenGL working group as well as the OpenGL working group, meaning the extension has been written and can be implemented on mobile platforms as well as desktop platforms. The first example of that is texture compression ASTC, adaptive scalable texture compression. Very flexible format between less than 1 bit per pixel up to 8 bits per pixel. Very powerful, very high quality compression format where Khronos basically says, we believe this is the future. We're going to release this now. There's no hardware, so I don't know, capable of actually compressing or decompressing this, but we fully expect that will show up in the future. That's why we're doing this. And also think the sweet spot here will be the 1 and 2 bit per pixel texture compression ratios. Robustness isolation, an ARP extension that provides even more guarantees on top of the robustness extension we already have. It basically says what can and cannot happen when your application does something bad and causes the GPU to reset, for example. The GPU resets, the only thing that can be affected is your application. Anything else running in the system cannot be affected. Other applications cannot crash, other applications cannot lose their data. The system cannot crash either. Moving on, we have OpenGL 4.3 reference pages up. I just heard. Yeah, that's awesome. Graham Sellers, Graham, where are you? Can you stand up for a moment? Graham spent all his personal time, free time, spare time, and no sleep time on getting this done by today. So thank you, Graham. If you download the 4.3 spec, you notice probably that it has been rewritten and reordered. We try to make it more logical, easier to read. Introduce high-level concepts first before we use them. So, for example, objects in buffers. We looked at, we pulled out the error codes and put them in a clear to read section and many more changes. So Give us comments, go to the forums, let us know what you think of the new order. Okay, so in conclusion, lots of new stuff in 4.3. OpenGL uses and will reuse and rise sharply with WebGL and ES and Linux and Windows. Great to see that. OpenGL is 20 years today. Okay, what's going to happen the rest of the evening here? After Rich is done, this is very important, guys. So after this, we get Bill, then we get Rich, and then we need to do a toast to OpenGL. So get your drink later, come back here and we toast, and then Kurt will do his presentation. But now, some trivia. Okay. So I use a mobile device too. Okay, I'll start it off for a inside book. Please raise your hand. Don't scream out the answer. Just raise your hand. I'll try to find the first one to raise your hand. You know? What was the first OpenGL object? Over here in green.
Texture object.
I'll take texture object. Sure. Yep. Coming up over here, I'll get you a book here. Okay. Which OpenGL version, and again, raise your hand, don't scream it out, has added this texture object? Yeah, in the back. Yeah, very good. All right. We'll do one more for a, well, okay, we'll do this one first. How many OpenGL specifications have been released so far? Raise your hand, come on. Yeah, whatever. 12? Nope, that's not correct. Anybody else? Yep, we're
14?
14, not correct. Nope. Yeah. 11, nope. You guys are not efficient in searching there. Say again? 12, nope. It's higher. Go ahead. What is it? 9? Nope, it's above 10. Okay, the green over there. 17 is correct, all right. So for this awesome, not so efficient search algorithm, you get a great candle you can use at the party. Next up, next speaker. Bill, where are you?
Good evening. I'm Bill Licea-Kane. I work for AMD. And yes, I know this is a green shirt. Don't read into anything with this. This is the Boston lime green color, just making it clear. This is the Boston Siggraph t-shirt. I work for AMD. I like working with NVIDIA guys. So some brief personal notes on this anniversary. 1912. Fenway Park opened. I'm from Boston. You have to celebrate big events like that. 1962. We're in LA. Dodger Stadium. 1982. Siggraph finally came to the East Coast, to Boston, and I was young and I attended my first Siggraph. It's pretty cool. 1992, well, we're here celebrating what happened then. OpenGL 1.0. But for personally, right before the OpenGL 1.0 spec was released, my son tried to be born. And so I remember racing to the hospital with my wife. The scene was mostly reminiscent of what you see with a Formula One pit stop, with multiple doctors, nurses, and everybody on every corner, everywhere, strapping, injecting, doing all kinds of amazing things. They managed to stop the labor, and I called up work and said, I'm not going to be coming into work for a little while. My wife has full bed rest, blah, 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 blah. The following week, I went back to work for just a brief moment. My manager at the time gave me a beeper. Remember that technology? Said, "You're on call. We're never calling you." She handed me a spec that was OpenGL 1.0 and said, "If you feel like doing anything work-related, read this." And so I got permission to go back home, take care of my family for the next 3 weeks while full bed rest actually worked. My son came more or less on time. And believe it or not, I got to know that OpenGL 1.0 spec better than I expected, because as much as you have to do all kinds of stuff with taking care of family and everything, every once in a while somebody is asleep and you say, "Okay, I'll take a look at the spec again." So it was really an enjoyable experience for me. 2002, the first course on OpenGL 2.0. We still were just prototyping it at that point. OpenGL GLSL actually was born just up the street at Wilshire Grand the year before, when the whole project was proposed. Oddly enough, the proposal to have the Wilshire Grand Hotel be declared a National Historic Landmark as a result was summarily rejected. They're tearing it down anyway. Also that year, our Vertex program, our program came about. So, OpenGL 2.x. The actual spec itself was September 7th, 2004, and the update to it for it came approximately 2 years later. The early days of programmability with OpenGL shading language were very limited devices. Effectively, you had some kind of floating point, Vec4-centric programming units. You had very little memory you could play with, and often you had very little instruction stores and data stores as well. And yet we designed the GLSL shading language to be forward-looking, and so that actual version of the shading language made it through a couple generations of hardware as they got more capable. Effectively, the minimum maximums were growing, and people were not needing to worry about things so much. In the early days, we would fall back to a software shader if your shader was too long for you. We got a lot of complaints about that, because fragment shaders in particular took a long time to complete if you filled out the software. OpenGL 3.x came through 2008 through 2010. That was the generation that added in much more capable shading units. Full floating point FP32 IEEE-like math in both vertex and fragment and geometry shaders. Much larger amount of constant memory that you could access through uniform buffer objects. The wonderful transform feedback to begin to do a bunch of loopback paths through the vertex engine. And that really became almost like the sweet spot for working with OpenGL, and now it's the basis for OpenGL ES3.x. And then 4.x, this is where this, over the past 2 years, effectively we've generalized things even more so, giving you finally read-write access to large quantities of memory other than what your pixel wants to write. And that's really been the fundamental thing that's been happening with the past couple of years there. By making the memory model a little bit confusing, but very, very fast, we can end up with not turning it into a serial instruction unit. It's still a very much parallel processing model. The writes and the reads that you do to this large amount of read-write memory may or may not show up when you first expect them to, but they will get there, and you have some control through barriers and fences and things like that to say when it's going to end up getting there. So, cool things that you never dreamed you could do with OpenGL. I'm going to just leave you there with this one thought. Everything we're doing with OpenGL are cool things we never thought we could do with it. It's been 20 years, and let's have another 20. Thank you very much.
Thank you, Bill. I wasn't expecting that answer. Right, two quick trivia questions. One for an OpenGL Insights book. Which version of OpenGL was the program pipeline object introduced? Yeah, the black shirt there. 4.2 is not correct.
Oh, he said 2.0.
He said 2.0? That's still not good. Thank you for the correction. He was first here. 3.2? Nope. The program pipeline update. What's the version of GL? Yeah. In the black shirt there, behind, arm up. Say this again?
1.4.
1.4? Nope. Yeah, the back there. Not 2.1. Come on, guys. We're almost done. I have 17, but a few more to go. I see just a hand, 5 fingers up there in the middle there. Say it again. 1.1? Yep, over there. Nope. I think I'm going to skip this question, guys. Horrible. I was going to ask you guys a harder one for one of the quadros. I'll try anyway. So what I need from you, 1, first raise your hand or read out. 2, here's the question. Name me 2 tokens like GL_foo whose value is 0. Yeah, you raise your hand here first.
GL invalid value and
GL text 0 and GL invalid value. I'm not correct. Nope. Over here. And the way in the back there. Yes, that's you.
_0 and
Getting there, but partially correct. Nope. Okay. Over here in the last shirt.
GL_null and GL_0.
0 and no. I don't think there's a no. You almost go no. So no. Okay. In the back there, and 5 fingers. You almost go what? Did you say no? False and? Yep, false is 0, that counts. Come on over here. Okay, Rich, where are you?
So the first thing we're going to do is show Left 4 Dead 2 running on Linux. This is Ubuntu 12.04, whenever they're ready. And this was basically Rick Johnson playing about 2 weeks ago.
Ooh, I know one store we can stop out along the way, get ourselves some real weapons. I guess the end here's finally paying off. This is way before Reloading! Let's go find that hole. Reloading! Reloading! I'm gonna reload! Reload!
Okay, so that was our short time. So guys, we're going to show the actual, so that was Rick playing about 2 weeks ago. All the inputs to the engine were recorded to a file and we played it back from the engine. We're also going to show a time demo. So this is going to be the same recording played back at the fastest rate this laptop is capable of doing. So it should go a lot faster and it shouldn't have sound. So we ran this probably 1,000 times in the last few months as part of our experiments. Okay, so this is what we call a time demo. Same thing, except it's not real time. It's not synced to real time, basically. So it's just feeding commands down the pipeline as fast as possible. So that's pretty deterministic. We can play that back on different hardware and get pretty much the same GL calls. There's a few problems with the limbs of zombies. Occasionally they'll be in slightly different positions because of physics. But other than that, that's been our target workload. So when we talk about getting 300 frames per second with that time zone. We also have a much longer time zone we're using now. It's about 10 times longer, and that also actually gets a higher frame than that. So first I want to say that the Steam team actually ported Left 4 Dead to Linux originally. Dan Berger, there's Rob Barris, who's on the Tegra team at NVIDIA. He originally wrote a lot of that code. Jason Mitchell. So all the original code, they ported it to Linux, they had it working, and then we formed a team inside of Valve that took that initial bootstrap effort and worked on getting performance up. And I want to say that this has been a totally collaborative effort. I want to give a big thanks to NVIDIA, AMD, the Intel open source driver team, and the Khronos group, because without all the help that we've gotten, all the feedback, this would not have been possible. So this particular talk focuses on performance with the GTX 680. Our performance with AMD and Intel is also really high, but this has been a race for us, and we achieved the frame rate we were looking for with NVIDIA first. So I already showed you the short time demo. That demo, when you play back as fast as it'll go, it's about 940 million primitives, almost 1 million batches. It's a pretty good round number, so Rick did a good job. So right now we're about 11% faster in GL versus D3D9 on the 680. Going through all of the batch code on our render thread, I think there's probably another 5% or so performance we could get there that we're saving just in case. But right now we're going to concentrate on basically releasing this. So just to cover real fast how the source engine targets GL, internally the source engine for the most part thinks it's targeting Direct3D. We've added a bunch of extensions to make sure that when we actually go to GL, it's a good mapping. But for the most part, there's a one-to-one mapping between GL concepts and D3D concepts. So the translation layer that we're using does not defer draw calls. So when the original source rendering code wants to do a draw index primitive call, we immediately flush state and then call GL drawing as elements-based vertex. So there's no magic here. We're treating GL like we would treat D3D9. We've talked with some vendors about deferring draw calls, deferring uniform updates and buffer updates. And that would probably lead to higher performance, but the problem with that is we have a whole bunch of code bases we want to port this work into that are slightly different. And the other thing is it doesn't send a good message to our partners that you have to treat GL differently. Well, actually you don't, and we've proven it. So right now our translation overhead is around 50-50 with a multi-threaded driver from AMD or NVIDIA. We started at a much worse ratio. We probably started at 85% in our code, our D3D-esque layer versus GL, and we've squeezed it down, and I'm going to explain how we've basically done that. We've done a bunch of comparisons, very deep comparisons between single-threaded OpenGL drivers and multi-threaded OpenGL drivers, and we learned pretty fast that if the driver is not multi-threaded, it's not going to have much chance of competing against D3D. I'll show you some trace videos that we generated in a little bit that kind of help you visualize that. So when we started this effort, we had very little OpenGL experience. So the last time I used OpenGL was probably the late 90s and let application used for visualization purposes. So pretty much most of our experience was D3D9 or Xbox 360 or PS related. We realized that the source engine itself is just a big ball of mud. It's been through a lot of different titles. It's been massaged a lot. And GL is this very large API, and we figured it couldn't hurt to ask for help, and that's exactly what we did. So AMD, NVIDIA, they all sent driver developers right to our offices, and so did Intel. So one thing we did first is we focused on why is it that our engine in D3D9 mode performs so much more slowly than OpenGL. So we developed a bunch of tools we used to figure that out. We also used some open source tools, and we also use a commercial product called Telemetry to do that. Now, I gotta apologize, I'm not actually used to hearing myself give this presentation over a loudspeaker. Okay, so our process at Valve is very much experimental. We'll conduct experiments, we'll try to interpret them. That can be very difficult in our engine and with OpenGL. Our game is heavily threaded. As we would conduct experiments, and actually as we would measure our performance, the bottlenecks would actually shift around. So sometimes it's like principles from physics. So we'll go and measure something, and what we're actually measuring is changing, so it'd be really confusing. The driver server thread, drivers are typically have multi-threaded modes, and the driver server thread, the actual thread that's feeding the GPU, is mostly hidden from us. So we can only feel its effects on the pipeline's performance. We've actually found some ways of working around that, which I'll cover in a little bit, but it can be tough. And the source engine itself is extremely configurable. It can work on 10-year-old laptops up to state-of-the-art PCs. And it can be tricky because you think you're running a time demo with a certain set of configuration, but actually you might not be. You have to validate that. So I learned to be like a banker and trust, but validate and verify everything. So what I'm going to do in this talk is I'm going to quickly cover some of the tools that we used. I'm going to cover the batch trace recording mode, so you're able to visualize performance in E39, GL single thread and the GL multi-threaded. We also use, and I'm not going to show that in here, but I just want to give a big shout out to AMD about their Perf Studio tool, because that works right out of the box with our application. We were really impressed. So Gordon Selly and the team over at AMD did a great job with that. So the first tool I want to cover really fast is telemetry. So this tool allows us to visualize and measure pretty much anything on the CPU that we want, and we're starting to use it for GPU measurements as well. It consists of 3 basic components. There's a visualizer app, which was just ported to Linux specifically for this presentation, but unfortunately our Linux laptop is back there, and so I can't show it running on Linux, but trust me, it's awesome. But I'm going to show that in the videos. There's a runtime component. It's really small. You give it like a mega memory. It doesn't call malloc. It doesn't do, there's very few side effects with telemetry. It creates its own thread that also talks to a server application. You can run on a Linux box or an OS X box or a PC. Telemetry is an intrusive profiling system, so we actually have to add explicit calls into our code, into the telemetry API. So there's 2 things I'm going to quickly cover, and this is telemetry zones for CPU profiling and telemetry time spans. So these are telemetry concepts that you can pretty much map to whatever you want. For Left 4 Dead 2, for this effort, we mapped time spans to GL ARB timer queries, specifically the absolute timestamp queries. And the zones we mapped to sections of code, basically. So there's a lot more that we plan on doing with telemetry, and I'll cover that in a little bit. So a zone basically is an area of execution. It's typically a function call, but it can actually be anything you want. You can call a begin and end at arbitrary places in your code, give it a name, and it'll show up in the timeline, and I'll get to that in just a second. The zones are also hierarchical and nestable. So if you begin a zone with some name and you begin another zone, they'll actually nest naturally in the visualizer. And so here's a little bit of sample code I threw in there. I kind of copied this right out of their SDK. So it's basically TM enter, you give it a telemetry context, you give it a printf string, and then whatever. You do some work, it takes time, and then you call TM lead. So this is a screenshot of the visualizer running with our first capture. So when we say we were running at 6 frames a second, I'm actually being optimistic. We were probably around 5.8. So this is a 273 millisecond capture that my start made about 6 months ago. We were sharing with NVIDIA and AMD at the time and wondering why are our drawing elements calls taking so long? And it turned out there was a specific bug in Linux that caused the shader compiler in the driver to execute a lot more often than it should have, and NVIDIA thankfully quickly fixed that for us. Okay, so what I'm going to do right now is I'm going to run telemetry and just show you a couple captures from the time demo you just saw. So I just started the server, and I'm going to start the visualizer. The visualizer is an OpenGL application. There's also a plugin API for the visualizer too, which allows you to render arbitrary stuff with OpenGL right inside the visualizer. It's pretty cool. So the first capture, so the server manages a database of captures, and it's like an industrial strength tool. I don't know if I'd hook myself up to it. If it was a light support machine, I don't know if I'd hook myself up to it, but it's really pretty. So I'm going to get a capture here. We made about 3 days ago. So what you're looking at here is kind of an overview. The y-axis is time. This is milliseconds per frame. And each line there, basically, of this graph is a single frame. So I'm going to select a frame at the beginning. So the engine, our source engine is multi-threaded. So this is the main thread right here. And we're not going to pay much attention to the main thread because it's not doing OpenGL stuff. So we're going to go to the render thread. This is our thread pool right here. So you can see that I'm basically browsing all the threads in our app. Real fast, the flow of time in telemetry is from left to right. I can zoom in and out. Unfortunately, I don't have a mouse, so it's kind of tricky to do that. But I'm going to go look at. Here's our render thread. And I've spent the last 4 months of my life looking at captures like this, so I've just zoomed in. Okay. And now I'm going to zoom in even further. So now I'm zoomed in at the sub-microsecond level. And one of the first things that we wanted to do while working on this project was account for pretty much every microsecond on our render thread, just to understand what is going on there, why. So you can see there's a whole lot of GL calls going on here. So Source Engine is targeting a D3D-like API. And you can see here's a draw index primitive call in this frame. And internally here, it's going to flush some draw states, and that involves GL uniform calls, GL bind, buffer ARB calls, etc. And eventually, it's going to do a GL draw range element. So I got to slide over a bit. There we go. So here we go. So here's the GL draw range elements call. So this is repeated over and over again. So we focused a lot on basically reducing the size of all the telemetry zones inside of our draw path. So all the hottest paths we focused on. There's also buffer updating paths, FBO paths. So let me show you one more quick capture. So we just added ARB timer query integration into our engine that creates time spans in telemetry. So I'm going to go quickly. I'll show you some time spans, and then I'll go back to my slide, which explains probably in pretty good detail what they are. So I just skipped all the CPU tracks. Now I'm looking at the time span tracks. So time spans are like zones. They're areas of execution, but they can be very long. They can span multiple frames. They're not nestable. I'm going to zoom in really far here. Attempt to. It's not letting me zoom in here. Got to apologize. I practiced this with a mouse, and so I'm using a Windows laptop with that. Well, in this case here, I have a whole lot of time spans. I hope you can see that. This is actually all of our GPU activity. So we're kicking off commands on our render thread, and over here it's being processed by the GPU. And I know it's not very compelling, it's just a big blob of gray. So let me go back to the slide. So this tool has been invaluable. We're going to keep on enhancing it, so enhancing our integration with it. One cool thing you can do is you can create arbitrary blobs in your game, send it down to the server, and then write a GL plugin inside of telemetry, which allows you to visualize those blobs. So what I'm thinking of doing is capturing the current GL state, frame buffer captures, just send as much stuff as I can down to telemetry so I can use that as a debugging aid. So I kind of covered most of this. We just started to use timer queries, and the reason why we added it in there is because the server thread of GL drivers is for the most part invisible. I can feel its effects, I can kind of do experiments and see things change, and I can kind of get an idea that the kernel is switching the threads that are probably inside the kernel, the server thread of the driver, but I can't really measure it, and I wish I could. Well, ARB timer queries actually allow us to do that indirectly. So when we send down a timestamp query, the server thread will eventually get that and then send it down to the GPU, and then we can query that, we can get that time back, and we can convert that to absolute time put in telemetry. So that's the one tool we use. That's a commercial tool. This tool here is something that we whipped together in a few days. This is called, for lack of a better way of describing it, batch tracing. So real fast, I'll just describe what it is, but this is actually probably better just shown like this. So we modified the engine to generate PNGs in real time. Then we added some APIs, that can render into a bitmap, and then every frame we just blast that out as a PNG file. Then we used an open source product named VirtualDub to basically take those PNGs and allow us to scrub them and make videos. And I'll show you an interesting video in a second. And so what we were able to do is focus on just the part of the workload that differed between D3D9 mode and OpenGL mode. We know that the engine's been optimized really well over many years to work on x86, so that wasn't our problem. So we can visualize a whole bunch of things here. Here's kind of a guide here. On the very left, at first, every scan line is a batch. So every scan line corresponds to either a clear or a GL draw range elements. We have some red lines.
That decision to not go down a path of having it be a protocol extension to a specific Windows system was fundamental. Actually, I was collaborating with people at Pixar, working with Pat Handerhand, considering whether we should try to throw them together and do something, and we decided we wouldn't, so they did RenderMan and we did OpenGL. The world would be a different place if the decision had been made differently, I guess. And finally, it's not a descriptive kind of a level. There's a lot that FIGS was more or less a descriptive level of doing graphics. OpenGL is imperative. You say what you want to happen, not what the reason. What you want it to do, not what you want the generic result to be. And it turns out that that's just the right thing to do for the lowest level of a graphics architecture. There's nothing wrong with scene graphs, they're wonderful things. SGI did a bunch of them. You build them on top of a low-level architecture. You don't try to make them be the low-level architecture. So those kind of decisions got made correctly. And as a result, it was cross-platform. And we also, I think, really wisely checked around and found out that people wanted to use Windows systems the way the Windows systems were specified. If you're writing a Windows app, you want to use Windows interfaces. Heaven help us. If you're right. But that's the right thing to do. And if you're writing, at the time, a Unix app, you're going to use Unix stuff. So we ripped all the UI stuff out of IrisGL when we did OpenGL, and that was also the right thing. So all that's interesting. I think perhaps the most important thing about that level is a little more subtle, and that is it's clearly way above the level of a CPU instruction set architecture. Right? So usually when people hear the term architecture, that's what they think about, right? IA 32 or something. But an architecture does not have to be an instruction level. And for graphics, it's a really great thing for this community, and I think for a broader computing community, that we did set this level higher. Because A, it allowed a whole lot of innovation by some of the people in this room who are implementing these systems that just isn't as possible if you've got the level of the abstraction too low. And B, it allowed data parallel computing to become ubiquitous. And that is a big deal. That's how parallelism, it's hard to say, is going to take over the world. And it's the reason why GPUs got faster than CPUs faster for so long. I think things are starting to even out now, but an amazing capability has entered into the lexicon of people doing programming. And it's not just about graphics anymore, but we really helped as a community allow that to happen by working with a standard API that allowed the parallelism to be implemented underneath. Okay, so enough about techie stuff. Let me say just a little bit about people. So OpenGL culture is specification driven. You heard about it tonight, right? The pages are out, the new spec is rolled out. It really came right from the start. The reason that Mark Siegel's name is above mine on that specification is because he wrote it. Right? It really was his work, and it was fundamental to all of our success, I assert, that it's a really well-written document. Cared a lot, we worked very hard on it. There's a bunch of details. It's got a, those of you who've read it, I hope that's almost all of you at some level, there's a state diagram, or state tables in the back. And those tables tell you everything you need to know about every stinking bit of state in the whole machine. And it's a big deal. Right? With that kind of specificity, it's possible to make things compatible. It's possible to make things work reliably and portably and all the rest. So we made sure the state tables were in there. We made sure there was a discussion about invariants. Maybe some of you haven't read it. You can get away without it, but you can't really use OpenGL as the vector processor system that it is if you don't count on a promise that certain changes in the rendering vector state won't change the pixels that get tickled by the drawing. There's a bunch of details in there that were thought through that allow OpenGL to be used really as an imperative instruction set and not just a way to draw points, pixels, or polygons. We designed extension templates because we're really serious about making sure that every extension covered all the bases and got things off to a good start. We figured out that if extensions had to refer to each other, if they didn't refer to each other, you wouldn't know how they all work, so we invented the index. I don't know if we're still using the index, but these things got stuff off to a good start. And then as things have gone, also really wonderful things have happened. So I made this in 2008. It's just kind of an interesting character count comparison. There is a lot of blood, sweat, and tears by a bunch of you in this room, as well as others, to take seriously writing extensions as full specifications. There's just a lot of text about that. One of the beautiful things that happened, again, I'm not sure who did it, but it certainly wasn't us when we started, is people figured out that we really ought to be keeping track of the issues and their resolutions in these specifications. We really ought to also have a usage example in all of the extensions. Those are wonderful additions. So I felt like we got things off to a good start, but the community rallied behind this and made it better, which is wonderful. And finally, I couldn't resist walking upstairs at Siggraph and just taking a quick look at how many OpenGL publications are out there. So these aren't specifications, but this stuff's really important. And I suspect, I don't know it for a fact, but I suspect that you won't find as many direct 3D things. So it's consistent with the culture that we've created with OpenGL, that not only do we as an organization and as a team that's building this thing take specifications seriously, but the whole world takes it seriously. So this is a really important thing that I think has hugely contributed to OpenGL's success. And then finally, so I dragged up pretty much the only picture I've got. The people in this picture poured their hearts and souls into making OpenGL a great thing and doing the right thing. I'm sure that many of you in this room have also poured your hearts and souls and your integrity and your technical skills into evolving OpenGL and making these good decisions that have allowed it to be successful over all these years. So I just wanted to give you my personal thanks for all of that concern and care and greatness. I deeply appreciate it. Happy 20th anniversary, OpenGL. Thanks.
Thank you, Kurt.